So, what's so smart about smart instrumentation? I'm Mike Glass with Orion Technical Solutions, and I'm going to try to answer that question here. So, the first thing to understand that we have to understand how old instrumentation prior to the smart instruments actually worked. And that's what we're going to cover here on the next slide. Okay, so the older analog electronic instruments typically were driven with operational amplifiers, these transistor-based chips, basically, kind of the early days when they were really just starting to get this electronics thing all lined out. Um, and what they would do in order to convert the sensor to an output signal that goes to the controller, your 4 to 20 or whatever, they typically it was for linear signals. There's a typical setup. You have to multiply it, and then you have an adder that moves it up or down. And with those two, you can get that straight line, that conversion, if you will, or transfer function anywhere you want. So basically, what they had is they had a gain amplifier, which was basically our span adjust, the little S adjustment, and that would adjust the steepness of this blue line here. It would make it steeper or shallower, but it would change the slope. And then the signal would feed into another circuit where they would adjust the offset or the zero, the Z adjustment. And that would simply add some amount to the whole line or subtract it. It would move the whole line kind of in parallel up or down. Well, basically, with those two adjustments, you could adjust everything. And it worked, but the problem is both of these analog electronic chips, transistors, are not perfect. They can't make them perfect. Only with a microprocessor can you get that level of differentiation where you say, yeah, this is the answer and there's no in between. So basically, this is one of the reasons that they had problems with these older instruments, why they're not as accurate or stable as some of the newer instruments. I'll explain more on why the newer are better later, but the fact that to add extra circuitry, they had to add another amplifier, some kind of circuitry that would have analog electronics. They couldn't do things like compensation circuits. They couldn't add additional linearizing, for example, on thermocouple calculations. That's a pretty long polynomial equation. It's a very complex equation if you really try to get accurate. Well, they would go to about 3 layers deep and call it good enough because there's a point where you add more electronics, you're adding more errors into the system. And so it was a point of diminishing returns, but the fact they could not compensate for things like temperature, time, etc., made those circuits tend to drift by up to a 0.5% per year or more. And that's actually where a lot of our instrumentation calibration standards come from. A lot of plants are still operating at a 1% tolerance. Everything was kind of based on that then. It still is, or sometimes 0.5%. And even your calibration frequencies are based on that in a lot of places. Sometimes regulatory drives that, but uh, so that's the basic problem with the old instruments. In a minute, we'll talk about what's different with the newer instruments. So as I said, typically these older instruments use transistor-based op amps to do all the math. Uh, and they obviously drifted a lot due to temperature changes, just over time. Power supply voltage would have a big impact. Power supply warming up would have a big impact, or the transmitter itself as it stabilized temperature. The electrical load, so depending on how many milliamps and what the load on the transmitter was, and many other factors. So these instruments drifted considerably. Uh, Basically, a lot of those instruments drifted up to 0.25% or 0.5% per year. Um, and interestingly, 0.5% per year is what a lot of the calibration frequencies was based on. So a lot of plants still to this day are doing annual calibrations on instruments that drift a fraction of that speed, just because it's, well, that's the way we've always done it. Sometimes there's other reasons, such as regulatory, or it just makes sense on a SIS, on a SIL3 transmitter. You're going to do things more frequently. But a lot of times, no one's just taken a step back and looked at it. We have another blog on that topic, if you're ever interested. Okay, so how do the modern smart instruments work? Let's talk about that. So the key components of a modern smart instrument, you have your input, that'd be a sensor, thermocouple, RTD, might be a pressure sensor, a little piezo disc, might be a capacitive element in a DP transmitter, but there's some electrical parameter that's going to be measured, and then that is sent to the analog to digital converter. Um, that is going to send, you can see all these bits here, there should be 16 bits on a typical instrument going into the microprocessor. The microprocessor is the brains. The microprocessor will do all the math and calculations and all the diagnostics, determinations, etc., all the scaling, filtering, you name it. We'll send that to the digital to analog converter that actually provides the 4 to 20 milliamp output. A lot of instruments will have an optional display as well. We'll talk about that. And they also typically, a lot of them have a modem for like your 4 to 20 milliamp heart signal and so forth, which would actually then talk to your digital to analog converter. Or sometimes you have different communications like foundation field bus where you don't even have a 4 to 20, it just comes out of the modem. And then we'll talk about how the detailed operation of this is in the next slide. So there's a lot going on in this instrument. So let's start at the beginning. Basically, the the parameter, whatever it is, RTD, resistance, a thermocouples, millivoltage, etc., comes in. That analog parameter is converted to a binary number. You can see there's a big binary number. That binary number represents something to the microprocessor. It's essentially scaled in a digital numbering scheme. That microprocessor does all of the filtering, the scaling, basically your URV, LRV, etc. Sometimes it'll do square rooting, square root extraction. It can do statistics things like averages and moves, mean, max, min. It can do various math like finding the difference between two RTDs, finding the sum of two different two different process variables. It can do compensation as temperature changes, etc. It can do diagnostics, really powerful diagnostics. Some of these instruments, they're not even doing a fraction of what they could and should be doing at most facilities. And they can even do logic and so forth. The power is pretty incredible. If you read one of those manuals, if you've never read the Rosemont 3051 manual, you owe it to yourself to read that. Your mind will be blown at all the things it can do that you're probably not doing at your plant. So along with that, the microprocessor it'll look at the upper range value and the lower range value that you specified. Those are the 0 and 100% points, and it determines what percentage that output should be at. And it'll send that signal to the output, or the D to A, the digital to analog, we typically call it the output, which will actually adjust the 4 to 20 milliamp signal. The analog to digital and the digital to analog converters nowadays are way more precise, stable, accurate than they were back in the 80s, 90s. So for that reason alone, these instruments are way more accurate. But the biggest reason is because all of the real math is done inside the microprocessor, and that is extremely accurate by doing that digitally. They typically have that display screen. Not all of them, but some of them will have a display. It's like your M4, M5 option on Rosemont. Other ones have similar options. You basically typically see the PV, the process variable, which is your input. That's what it's seeing from the analog to digital. It'll It'll indicate the percent of the URV to LRV range. So it says 50%, you're halfway. And it'll tell you the expected milliamp output typically. It a lot of times, I know on the Rosemonts it just says MA, it says milliamps, and people will see that and see 12.0 and say, oh, it's 12.0, we're good to go. You've got to check that 20 milliamps, because that is just telling you that the microprocessor, that it's good on the A to D. If this digital to analog is bad, this signal may not be at 12 milliamps. Even though it says 12.00 right here, it might be 11.5 over at the output. So that's why we actually, all of our procedures always say to check the output. Sometimes you don't have to do that, for example, on field bus instruments, or depending how your maintenance is laid out. Sometimes you're just checking this part. But if you're just checking the PV, know that you have not checked this, and you will occasionally need to check the rest of that signal. And it even can fail and drift and everything along the way. And I have blogs talking about that. Everything from a little bit of water in a J box or in a conduit run, the typical PLC analog input cards actually drift. They drift faster than these instruments, ironically. No one seems to know that, but they do. You can look at the specs. Um, so the modem actually develops a digital signal for communications. Typically, on a lot of our instruments, that's going to be that heart signal that rides on top of the 4 to 20 milliamps. But it could also be foundation field bus that just goes direct. That modem allows for two-way communication. So not only can it send out information, additional data, in addition to the PV that you're sending out over your signal, but it can send secondary and tertiary variables, things that are really helpful sometimes. So pretty powerful little instrument. And individual instruments have way more features and functionality, but this is kind of the typical. So some of the advantages of smart instruments as compared to the older instrumentation we used and still do use, actually. Because a microprocessor can do nearly perfect math within our range of ability to measure, it's 1 part in 65,536 for a 16-bit system. That ends up being about 0.001526% of the span. That's pretty precise. You're probably not going to have equipment that can actually measure that small of an increment or an error. So that microprocessor math, it's ones and zeros, and it's either on or it's off, and it has all these algorithms to keep it from getting confused and being almost or kind of sort of, which analog does, right? Analog drifts, it's not exact. So for that reason, it has those calculations are incredibly accurate and stable. They don't they don't have those drift and other problems. That is the biggest benefit of the smart instruments or using a microprocessor, is that all of the math is as perfect as you would be able to even realize. They're typically from 10 to about 100, up to 100 times more accurate than the op-amp based predecessor, which is a remarkable contrast, and yet a lot of times, like I said, it's not even factored into your maintenance programs. Additionally, microprocessors can easily handle all of the filtering or the damping, along with a lot of helpful math functions, statistical analysis, scaling of the output, obviously. They can do square rooting or square root extraction, and lots of other math functions. But another huge one is it provides for advanced diagnostic capabilities, which is very powerful on most smart transmitters, as well as digital-based downloadable configurations and setup. So you don't have to go and dial knobs and so forth. You can actually just download the configuration, which if you're not using that, you're really wasting smart transmitters, and a lot of sites aren't. Through digital comms via heart modem or equivalent, the microprocessor can also get data so that you can send it information, you can change the configuration without having to go up on top of the flare or whatever it is. Um, and it can also send out those alerts, the diagnostic warnings, etc. That RTD, maybe you got a dual RTD on a Rosemont 3144, and one of the RTDs has failed or is acting up, it's failed over to the backup. It'll let you know instead of you finding out when the second one fails. I've seen a lot of sites that's exactly what they have. They got the dual RTDs, but they got no way to know. There's nothing set up to tell them. So basically, uh, it's kind of redundant, but it's really kind of wasting the instrument. Um, and it can also send out, like I said earlier, secondary, tertiary variables over the data stream. So very, very powerful little instrument. So some conclusions on all this. Smart transmitters are not only more accurate than the prior instruments, they also utilize the power of the microprocessor to enable advanced calculations, processing, analytics, diagnostics, and two-way communications. It's important for instrument and controls professionals, techs, engineers to fully understand these differences between smart instrumentation and older analog electric or even pneumatic instrumentation, so they don't make assumptions that lead to mistakes and problems. And frankly, a lot of those mistakes and assumptions are happening, even with brilliant engineers, brilliant technicians, that I would think would know better, but they never get the training. How would they know? They just get new stuff, and the vendor says this is what's good about it, but they never slow down and talk about actual smart transmitters and so forth. They're usually focused on more of the detail level. Um, a lot of a lot of technicians and engineers get confused by certain points on smart transmitters, such as not knowing what the PV indication on the display shows or means, or how to use it when they're troubleshooting or performing calibrations. They misunderstand what the milliamp indication on the display means or what it's used for. And tip, as I said earlier, it's not the actual output current, as a lot of people seem to believe. Understanding when a sensor trim is needed versus when an analog output trim is needed. Um, Understanding how the upper range value and lower range value should be set up, and understanding that they are not the same thing as the older zero and span. I've seen techs use these even on like temperature instruments and other where they kind of fudge the URV and LRV to get what they want, and that's totally not how that works. But it happens pretty often when I was doing assessments. I used to be surprised how often I would see that, even at sites that were pretty high paid, pretty somewhat well trained techs. You still run into that. So. So, yes, we do cover all these points and many other commonly misunderstood topics and issues in the INC world in our INC courses. Through decades of working in and doing training, doing assessments in the INC field, we've developed a pretty strong catalog and idea of where the gaps and weaknesses are that cause problems across a wide range of industries, and we incorporate those learnings into each of our courses and in all of the content. We teach all of this via hands-on training so that students actually get to see, experiment with, and apply the concepts in real-world ways so they can ultimately return to work more skilled, more competent, more capable, and more confident. Our ultimate goal is to improve the capabilities, right, to solve the problem. And we found over the years, if we do that, we do well. So check out our courses and our other educational services today at www.orion-technical.com. We do more than do training courses. We also do we do competency work. We can do screening of new hires. We can do set up training programs, both kind of online, individualized, group, small group. Um, we can do a lot of very helpful things in the INC and electrical and those kinds of areas. So check us out today and give me a yell, Mike Glass, anytime if you have questions or would like to chat about any of that. Thank you.